The sea surface reflection has been a challenge for the industry since the marine seismic was invented in the 60s.
In many ways, removing the marine ghost has been a sort of holy grail for this business, so it's been a problem that everybody's known has had to be solved or has wanted to solve.
Today we have the ghost that kills most of the low frequency and also provides a notch in the spectrum. If we could have motion sensors together with hydrophones, we could actually get a completely new streamer that could solve many problems we have in the industry today. Well, for me it started in a conference where I heard about some trials that has been done with the Navy where they used motion sensors in a towed array. And when I came back to my office, I discussed it and said we should try it out, even though no one really believed it would be possible to do it. I think it was a lot of different pieces coming together because we had worked a lot in the past with ocean bottom systems.
Ocean bottom surveys typically use cables, which contain hydrophones capable of detecting pressure waves, alongside geophones which detect vertical particle motion. The seismic source provides a frequency range that maximizes both resolution and penetration into the subsurface. Typically, this ranges from 3 to 200 Hz. To put this in context, the lowest note on a piano is about 30 Hz, and 200 Hz is around the middle of the keyboard. Ideally, the entire bandwidth of the source would be recorded as the seismic wave passes the sensors. But this ideal setup has always suffered from a ghost phenomenon. An upcoming wave exerts positive pressure on the hydrophone, and a positive motion is sensed by the geophone. The wave is then reflected at the sea surface, reversing the polarity of the reflected wave. The hydrophone reacts to the now negative pressure, returning a signal of reverse polarity. The effect of the negative wave on the direction-sensitive geophone produces a motion reading of the same polarity as the original upcoming positive wave. When these signals are summed, the result is an increase in the amplitude of those with the same polarity, and the opposite polarities of the ghost cancel each other out.
While I was able to find a solution for the ocean bottom cable where the sensors are stationary, there are no vibrations due to towing, I knew that finding a similar solution to the towed streamer was going to be extremely difficult.
The interesting thing is that the first test we did was with a small streamer section in our test tank. And we had a small source and we tried to just see the principle, how it worked. Then we did another test in the Gulf of Mexico. That was the first really, I would say, test we did with hydrophone and motion sensors in a streamer section. And there was quite a lot of current there, so it was quite noisy. Got the data back and it didn't look good. I was really very kind of discouraged by the results until I finally spent some days just carefully looking into the data and actually got some fantastic results.
Conventional towed streamer systems suffer from a number of issues which affect the quality of the survey data, particularly noise close to the sea surface, and the frequency notches introduced by the sea surface ghost reflection. Towing the streamers at shallow depths, typically around 5 meters, offers the highest resolution. However, here the streamers are affected by weather noise. Towing deeper, typically 20 to 25 meters, reduces the noise and offers increased low-frequency penetration, but at the expense of resolution, as some of the usable frequencies are attenuated by the periodic notches of the receiver ghost. The frequency content is also further affected by the source ghost. To overcome this compromise and to reap the benefit of deep tow without losing resolution required a revolution in instrumentation. And that is exactly what PGS has done in developing the GeoStreamer, the first ever dual-sensor towed streamer. Like the ocean bottom systems, the receiver ghost is recorded with opposite polarities by the two sensors. The ghost notches are at complementary frequencies, and so when combined, the ghost is removed and the full bandwidth restored. GeoStreamer enables marine seismic to offer both enhanced penetration and higher resolution without compromise. Taking the GeoStreamer from prototype to a robust and reliable seaworthy system required significant investment in large-scale manufacturing. The commercialization process involved ensuring the designs were optimized for mass production and the appropriate tooling setup. Tens of thousands of sensors needed to be manufactured and individually tested before being assembled into their respective mounts in the streamer bodies. They're then wired up and tested again before being covered in a durable sleeve that is then gel-filled to create the solid streamer sections. Curing in the Texan sun, kilometers of GeoStreamer are soon to be loaded into containers for dispatch around the world. The new streamers are easily loaded onto the vessels. One of the advantages is that spooling and handling is unchanged, and the vessel is quickly able to benefit from putting this new technology into action.
What we do with GeoStreamer is that we get the job done faster with a better product. So in reality, no downside. So like when we shoot in areas with harsh weather, you can get more work done within a season.
And what's exciting to us is just looking at that initial stack data already. Fourfold unprocessed stack data is seeing reflectors that we did not see on the previous seismic shot by another company with 60-fold processed data. This is quite incredible.
Most of the projects that we've acquired and processed around the world, we've been able to put GeoStreamer data in front of the customer and compare with what we call the legacy data which has been acquired conventionally in previous years, and there's always been a wow factor. So here's an example from West Africa. You see that the geology here is very complex, and some of the areas in this seismic data, you can see the faulting and the folding is affected by these quiet zones, which are the fault shadows. But with GeoStreamer, because of the fact that we're able to record so much more low frequency energy, you can see a much better imaging of the deeper structure in the section, which is where the targets are in this particular area.
The thing I think which has made me most glad is to see the results from reservoir characterization work, where we can see that the ability to predict rock properties from seismic data has improved enormously, and that's because of the inclusion of the low frequencies in the data. That is a really important change which the GeoStreamer brings.
Our plans for the GeoStreamer is to deploy this new technology for the whole fleet and for the new builds that we are putting in order, and to have a uniform fleet of vessels and streamers deployed globally.
It was rare in my career in geophysical research that I came up with solutions that not only improved the quality of the data, but also improved the productivity of the data acquisition process. This is one of those inventions. It's a double win.